We'll start the construction of Nicol prism with a brief note about the discussion what we made about the Nicol prism. Okay, so we have seen that when a light falls on a doubly refracting crystal like calcite, tourmaline, topaz, etc., it will split into two plane polarized lights called double refraction. And if you are able to eliminate one of the two doubly refracting rays, we will get the one ray which is plane polarized, because the two doubly refracting rays are plane polarized, having vibrations in perpendicular directions. So thereby, I will have to now find out how to eliminate one of the ray, that is generally O ray A, by total internal reflection. But anyone, can you tell me what are the two important requirements for total internal reflection? What are the two requirements to get total internal reflection for a light ray? Anyone in the class? You can share your ideas. What are the two conditions for total internal reflection? Roll number 11.
Yes, sir.
Yeah, can you tell me?
Yes, sir. The light ray must be traveling from a denser medium to the rarer medium,
That's
and
good.
the angle of incidence must be greater than the critical angle.
Excellent. Good, Chinmay. Now, these two we have to follow to get total internal reflection, and thereby we have to eliminate one of the rays. So that is what the principle of the Nicol prism. So to get this Nicol prism, the construction is, I'll start with taking a calcite crystal. So a calcite crystal whose length is 3 times its breadth, I'll take it. Okay. So I start with taking like that. That is the requirement for the vision or view of the to increase the view of the polarized lights. Therefore, in the construction part, what we want is we want a calcite crystal. Okay, so I'll take a calcite crystal, and this is important. The dimensions are important. Calcite crystal whose length, okay, length should be larger than its breadth. Length is 3 times its breadth. So we have to cut this quartz crystal in such a manner. A calcite crystal whose length is 3 times its breadth is taken. Okay, so that's a requirement. And not only this, what we want more is that to increase the vision or view, we have to take this crystal and ground it or polish it so that the angles in the principal section will change change from 71 degrees to 68 degrees and 109 degrees to 112 degrees. What we are doing is that if I take a crystal like this, okay, this is the principal section, suppose say this is the principal section I'm taking, and we have seen in the previous case that in the principal section the angles are 109 degrees and we have taken this as 71 degrees. These are the angles in principal section. So to increase the vision, okay, principal section, what I'll do is I grind them by taking a file, grind this one, okay, grind it. If I grind this one, this will become more flat and thereby I can see the vision of the okay, or angle of incidence, if I say, can be changed. And therefore, what I am doing is actually I am grinding it, okay, by some angle, something it. So previously it is here, but as I am grinding it, the angles are changed in the principal section. This will become increased to 112 degrees, okay, and then Here I have 3 degrees should less here, therefore 68 degrees will be there for nickel prism. Okay, we have to change this one. Therefore, we have to say that the crystal should be grounded. Crystal is grinded. We have to grind it, okay, or polish it or file it. You take a file and grind it. Okay, grind. Crystal is grinded. Okay, we have to grind it so that or we say simply we ground this. Okay, I'll write it here. Crystal is grounded so that angles in the principal section so principal section we defined it's a crystal cut perpendicular to the opposite faces and having the optic axis the principal section. Therefore, so that the angles in the principal section becomes 112 degrees and 68 degrees instead of okay, previously the crystal cut will have the angles 109 degrees and 71 degrees respectively. So that we will change them into this, and this what we are doing is that to increase the field of view. So therefore this grinding process, okay, this process increases the field of view. So after doing this, what I have to do it, I will cut this crystal into two parts. That means I have taken the crystal, okay, like this. This is the one we have taken after grinding, suppose say, okay, and this is now angle has become 112 degrees. Okay, this way has become 68 degrees after grinding. Now I'll cut this crystal along the diagonal perpendicular to opposite directions, okay, into two parts. So I am taking and cutting this, okay, I'm cutting this in the perpendicular direction like this into two parts, cut into two parts, cut into two parts, so along the diagonal. So I cut it so that it will become two pieces. That means I have a one piece, something like this. Okay, this is the diagonal. Along the diagonal, we have cut this into this. I have, okay, another piece like this. These are the two pieces we have this. This is a piece one, suppose say, this is piece two. I have cut into two parts. So therefore, the next step is after grinding, what I suppose is that we have to cut the crystal, cut the crystal into two parts along the diagonal, okay. And while doing it also, you have to see perpendicular to, okay, a diagonal perpendicular to the principal section. So we know the principal section we have taken. I have cut it principal section into two parts. So I cut them into two parts. And I suppose now this is P, I call it as, this is Q, and this is I call R, and suppose this is S. Now I cut it like this perpendicular to the principal section, and therefore we have now, okay, two parts. And these two parts I join them again, okay, I join these two parts again by using a transparent material, a gummy material like that. So join these two parts, okay, these two parts. After polishing the cut faces. So these are the cut faces. Okay. When I cut these faces, you know that while cutting, there will be small scratch like one, and the surfaces are not plain. Therefore, what I do is I polish these two surfaces. If I polish them, okay, they will become very, very flat. So we'll have a flat two surfaces like this. So therefore, I can now join them perfectly without any break, okay, or any irregularities between this. So I have polished them. So once you polish them into two different parts, I will join them. Why I am joining them? I have to achieve by some means total internal reflection. That's why I am joining. So to join that, I use a material called Canada balsam. Okay, join these parts after polishing the cut faces by using, okay, Canada balsam. Canada balsam. So Canada balsam is a gum-like transparent material. Okay, it's a transparent material which is having a refractive index. That is important because of to getting total internal reflection. So that it is less than the ordinary ray but greater than the extraordinary ray, because we know that ordinary and extraordinary rays will have different velocities in different directions. Therefore, in general, the ordinary ray in a calcitic crystal moves slower than the extraordinary ray. Therefore, the refractive index of ordinary ray is higher and the refractive index of E ray is less. To get total internal reflection, I take Canada balsam, okay, and so that the if I just join them by Canada balsam, whose refractive index is in between these two, therefore one of the ray is moving from rarer medium to denser medium to optically rarer medium, which will undergo total internal reflection. That is one important thing. So therefore, what I do is the refractive indices are important. Therefore, if I say the index, refractive index in the calcite crystal for O ray, ordinary ray, we generally call it as mu 0 is equal to, generally it is 1.658 is the refractive index of it. Similarly, refractive index of Canada balsam, if I take Canada balsam, okay, Canada balsam is a gummy like material, okay, balsam, yes, am I have to write, okay. So I take now here Canada balsam, I take it as Canada balsam. So Canada balsam will have a refractive index 1.550. Similarly, the refractive index of E ray in the okay, one calcite crystal mu is less than Canada balsam 4.86. These are the values. Now, how it works, we can explain by drawing a figure. So I am now taking here cut surfaces and joined by the Canada balsam. So I take here, okay, I just draw it something like this. Okay, so this is the principal section which I have taken. Now we will cut this into two parts, and I cut this into two parts. Okay, I cut this into two parts as I have shown you in the previous class, previous figure. So I draw it and cut into two faces, something like this. Okay, instead of that, I'll take different color here. Okay, I draw this. So I cut this something like this. Two, okay. So thereby, this is the cut part of it. Then I take the cut part. Just a minute. Okay, we have this. So we have a cut part here, and I also take to show the cut part clearly. I am drawing with another line, okay, to show you the cut part. Just a minute, it's not correctly coming. So I draw it something like this. Okay, so I take it here somewhere. Okay, 1 minute. Yes, switch off all of your mute yourself, all the participants. Okay, now I take this and keep this here somewhere. Okay, instead I'll draw here a line. Okay, to show you that the Canada Balsam interface is here, and this is called Canada Balsam interface. And we call this as P, Q, R, S. We have taken like this. This is Canada Balsam interface. Canada Balsam interface. Now, suppose say a light is made to fall on it. So I am taking a unpolarized light, and unpolarized light is made to fall on this. This is the unpolarized light falling on it. And as you know that this is a doubly refracting crystal. This doubly refracting crystal has a property of splitting the light into two plane polarized lights crystal, which we have taken here is a calcite. We have taken it as a calcite, and therefore the light which has fallen on it will be splitting into two rays, and the two rays I am representing by two different colors. Suppose say this is the one ray having vibrations in the parallel one, and this ray is nothing but we call it as E ray, having vibrations parallel to the principal section. And we have the second doubly refracting part of it, and that secondary doubly refracting part will come as a 2 and hits here somewhere because its velocity is different and having vibrations perpendicular to the plane. That's what we represented by this, and therefore I call this color ray as O ray. So now two rays are there. Now look at what about this. But you have to see here very carefully that whatever the light that is falling here should fall an angle which is equal to 14 degrees. This is most important. Angle of incidence for air and Canada balsam must be around 14 and 14 degrees. Otherwise, this ray, E ray, will not strike at an angle greater than a critical angle. Therefore, you don't get the total internal reflection. Therefore, this is important. The angle of incidence, this is angle of incidence. Angle of incidence. This is important for TIR. For TIR, total internal reflection, if the angle of incidence is this, then it strikes at an angle. Therefore, I say theta I, if I take it as angle of incidence should be greater than theta C. And therefore, we will get total internal reflection. That is first part of it. First part, to get total internal reflection, there are two conditions. One condition is that you should have the angle of incidence should be greater than a critical angle that we have followed here by taking the angle of incidence of 14 degrees limited to it, then it definitely strikes at an angle greater than critical angle. Okay. And then second part of is that it has to move from optically denser medium to optically rarer medium. Now, if I take this, okay, and I also show here the optic axis will be somewhere here so that their velocities are different. This is optic axis of the crystal. Now, okay, this is the optic axis. Now what happens? This ordinary ray is moving from the calcite whose refractive index here for ordinary ray is this. It is moving from calcite, which is high refractive index medium, to low refractive index, high refractive index to low refractive index. Therefore, it will undergo a total internal reflection and it gets here. It will not cross the Canada balsam and calcite interface and it will be absorbed by here only. This will be absorbed. It will not be coming to the other crystal and it is not transmitting. So therefore, we are able to eliminate O ray. Okay, here O ray is eliminated by total internal reflection at Canada balsam calcite interface, or we say here instead, okay, calcite Canada balsam interface, balsam interface. Therefore, as we are eliminating it, only E ray will come out of it. But however, the E ray is moving from, so it is moving from optically denser medium to optically denser, that is calcite. As it is moving from optically denser medium to rarer medium, okay, rarer medium, it has been eliminated by total internal reflection. However, if you take the same one for the case of E-ray, if I take E-ray, E-ray is moving, okay, E-ray is moving from rarer medium, optically rarer medium, okay, that is calcite, optically rarer medium, rarer medium to denser medium, denser medium. But if you see this, the optically rare denser medium is Canada balsam. So E-ray is moving from optically rarer because for E-ray, the refractive index is 1.486, whereas for Canada balsam is 1.55, which is a higher one. So thereby the Canada balsam is used as a medium to create total internal reflection, and thereby this ray will undergo a lateral shift, slightly a lateral shift, and comes out of the crystal here, having vibrations only in the plane, okay, parallel to the principal section. Therefore, the transmitted light is having only E ray. This is the transmitted light. This is transmitted light. So transmitted E ray, which is a plane polarized. Plane polarized. Therefore, the Nicol prism eliminates O ray and allows the E ray to transmit through the Canada balsam interface, and it will only come out of the next surface, okay, QS, which is perpendicular to the incident one PR. Thereby, okay, parallel. Thereby, we will get a plane polarized light. That's why the Nicol prism acts as a polarizer. Okay. So optically rare medium, hence E-ray comes, or we say transmitted, E-ray is transmitted. So therefore transmitted light out of the crystal, out of the crystal, which is a plane polarized, which is a plane polarized. Thereby, we say that plane polarized. Therefore, we say that nickel prism acts as a polarizer. So therefore, nickel prism, okay, therefore, nickel prism converts unpolarized light, incident unpolarized light into polarized light into plane polarized plane polarized light. Therefore, okay, nickel is a polarizer, is a polarizer. But we know the same polarizer can be used as analyzer. So therefore, nickel can also be used as, okay, analyzer. Only thing is nickel can be used as analyzer also. So how do I use it? So nickel prism generally is represented by the figure what we have drawn just like this. Okay, and this is the nickel prism I'm taking. Okay, and I suppose say I take another nickel prism also here. Two nickel prisms I'll take. So this is the another nickel prism I'm taking. And I suppose that this is nickel 1 and I say this is nickel 2. And I suppose this is the optic axis. I'm taking this is the optic axis. And this is the optic axis for this. I have not turned this anything. Okay. Therefore, we call these are optic axes. OA is optic axis. Okay. We call it as optic axis. Here also we have shown this is optic axis. We generally call it as OA, optic axis. Now, two optic axes are parallel to each other in the figure I have drawn it. So therefore, I say that here they are in parallel position or say parallel configuration or parallel position or cross position also we can say position. That means theta of the two n1 and 2 is 0 degrees. Therefore, when a light falls on it, when you take an unpolarized light falling on this, okay, an unpolarized light is falling on it and it eliminates one of the ray and thereby we'll get only one ray, the other ray, dotted ray gets out, okay, and it will come out as a plane polarized light having vibrations parallel to the second nickel. Therefore, second nickel passes them since the axes are parallel. So therefore, the nickel, second nickel passes them since E ray is having vibrations parallel to optic axis because I equal to I naught cos square theta, theta is equal to 0. Therefore, entirely I'll get I equal to I naught cos square theta. Since theta is equal to 0, I'll get I naught, light is passed. Hence, the second nickel is now making us to see whether the light is coming out of first nickel to the second nickel and the transmitted light is having certain intensity or not. So this we call it as polarizer P and this we call it as analyzer A. Now I take the same figure, but I see that here, okay, when they are in perpendicular direction, how they behave. So I will take now this as a analyzer. Okay, when the question will be asked, show that the nickel prisms can be used as polarizers and analyzers. So now I am taking here the same two. Okay, and now what I suppose here is that, okay, 1 minute, I just take another shape, something like this, and I draw here. Okay, so that they are in perpendicular directions. They are in perpendicular directions. So therefore, I now write that here, okay, I now take that this is the incident ray and I'll say this is the optic axis of the principal section and this is the principal section for this, which are perpendicular to each other. Generally, the crossed position will be shown like this in the figures. So we say this is a crossed position. Crossed position. Crossed position means that their optic axes are perpendicular to each other. That is theta is 90 degrees. Now I suppose that a light is coming and falling on it. So I take now unpolarized light is coming and falling on it. This is the unpolarized light. Generally we represented by a arrow, and it splits into two parts, E ray and O ray. O ray gets diffract, totally transmitted by total internal reflection, but E ray will come out of it, and this is the E ray coming out of it. We have vibrations parallel to the principal section. It comes here, but if you see it, they are in crossed position. So therefore, there is no vector of light vibrating in the direction of optic axis of the analyzer. They are perpendicular to each other. Therefore, outside we don't get any light. There is no light, no light, because we don't have a light vector vibrating parallel to the optic axis of the analyzer. We don't get any light out of it. Therefore, you can say that as by rotating the second nickel, you can check the intensity variation. Therefore, if you find any change in variation of the transmitted light by the second nickel, which is uh, called as analyzer, can be tested whether the incident light from the polarizer is a polarized light or not. Therefore, we say by rotating rotating second nickel prism, which we call here as A analyzer. Okay, by rotating second nickel prism, one can observe variation in intensity of the transmitted light of the transmitted one can observe variational intensity of transmitted light by the second nickel then we say then the incident light is polarized. We can say that, we confirm that incident is one. Suppose that there is no change in intensity. No change in intensity means that even though you are having by optic axis perpendicular to each other, suppose say incident light is like this, it's a parallel. Then if I take this nickel prism like this, only one nickel I'm taking, suppose say, if I rotate some direction, I'll get light out of it because there is a vector parallel to it. Still I rotate it by some other direction, suppose say I rotate it by 90 degrees like this. But still it is unpolarized light. Even though I rotate it, there is a perpendicular parallel component to this optic axis in their direction, because the unpolarized light is an unsymmetric light along its direction of propagation. That means all vectors are possible. In whatever the direction you tell, you will get a light out of it. Then you don't observe any variation. If you are not observing variation, no variation or no change in intensity, means that the incident light is not a polarized light, it is an unpolarized light. That means in this also I am getting, when they are like this, even I'm turning by some angle also I'm getting, means that there are vectors in unpolarized light in all possible directions. Therefore, whatever the direction you make or you turn the analyzer, you definitely you get a light out of it. But it is a plane polarized, but still there is a light. Hence, we say the incident light is unpolarized. Thereby, you can check whether the incident light is polarized or not by help of the second nickel, which we call it as analyzer. If you turn the analyzer by 360 degrees or so, or 180 degrees is sufficient, then you say that when the optics axis is parallel to the first Nicol called polarizer, then you'll get light. If they are perpendicular, you don't get light. In between, the light intensity varies as I equal to I naught cos square theta. If even though you are rotating, if they don't observe any change or any variation in the light intensity transmitted by the analyzer, then we can have a confirmation that incident light is unpolarized, because unpolarized light will have light vectors in all possible directions. Whatever the direction you turn the analyzer, you have at least one light vector vibrating in that particular direction of optic axis of the second Nicol. Hence, we'll get the light out of it. Therefore, you can give the action of Nicol prism as a polarizer and analyzer. So you may be asked a question, explain the action of Nicol as, okay, Nicol as a polarizer and analyzer. Polarizer, it is converting into this polarizer and analyzer. Analyzer. So this is the polarizer. Here it is polarizing the light, and this is giving you analysis action. We call it as analyzer. Okay. So therefore, the applications of Nicol prism is it can be used as a polarizer and it can also be used as an analyzer. Okay, both you can use it. That is important. But here also we can say by Snell's law, if I use a Snell's law here, okay, if I use Snell's law, you know that mu is equal to, okay, 1.68658 is the array, n1 by n2 by n1, and the other is 1.55 is the micro. So which comes out around, if I take this as mu is equal to 1 by sine c, I can take 1 by sine theta c, and thereby theta c in this case comes around 69 degrees. Okay, if you substitute this, mu is equal to this 1 by sine theta this, and the ratio if you find, you'll get a critical angle as 169 degrees in this. So thereby the Nicol can be used as an analyzer and polarizer. Then we have another important devices. Suppose say we have a doubly refracting crystal like this. Okay, light has incident on it. It has made into two parts having vibrations in the parallel plane and also in the perpendicular plane like this. Now I would like to create a path difference between these two rays, maybe 90 degrees or maybe 180 degrees or maybe 45 degrees. So okay, or then if I introduce some path difference between these two within the crystal itself, then the two rays will come okay, by an angle, suppose say 45 degrees. Then if you take here, this is the light vector, incident light vector, this is the O ray, and this is the E ray, this is the E ray, this is the sorry, this is the O ray, this is the E ray. So if I say A, I'll get A cos theta and I'll get A sin theta. If I make this as angle 45 degrees, that means E ray and O ray, and they are moving within the crystal, I make them with a phase difference of 45 degrees. Then I'll get A cos 45 and I'll get A sin 45 degrees. Okay. So A sin 45 degrees. Thereby their amplitudes are equal. That means if I have two plane polarized light with same amplitude, if they superpose, I'll get a circularly polarized light. I can produce circularly polarized light. Similarly, if I take them with different amplitudes, then I'll get a elliptically polarized light. Therefore, there are some devices which are called as wave plates. We call them as wave plates. So we will now look at wave plates. We'll see why they are calling as wave plates and how many types of wave plates are there. So we first talk about quarter wave plate. Quarter wave plate. What is a quarter wave? You know, this is the a wave. Okay. And you know, this is the amplitude A I'm taking. Okay. Maybe anywhere you can draw it. And this distance is we call it as lambda, one wave. This is one wave. But if I take half of it from here, you know that this is lambda by 2. This is lambda by 2. If I make it further half, I know this is lambda by 4. Okay, thereby a wave plate or a calcite crystal cut or a quartz crystal cut which introduce a path difference of lambda by 4 between O ray and E ray. The thickness you have to choose it, because if you choose the thickness, they move with different velocities. So E ray in one of the crystals, as you suggested, okay, if you take a calcite crystal, E ray moves faster than O ray. Therefore, as E ray is moving faster, it covers more distance than O ray. Now you choose the distance or we choose the thickness so that the E ray moves lambda by 4 advance of O ray. Then there is a path difference or phase difference of lambda by 4. If you make the crystal cut larger, thicker, then the path difference will be lambda by 4. Then we call it as half wave plate. Now we will see a quarter wave plate. So we will define a quarter wave plate in such a way that, okay, a calcite crystal or crystal plate, maybe quartz also you can take here. So a calcite crystal crystal cut whose thickness whose thickness is such that yeah, can you hear me, all of you? Okay. So we will now see the yeah, am I audible, all of you? Yeah, am I audible, all of you?
Yes, sir.
Yeah.
Yeah,
Now,
sir.
yeah, next important point is quarter wave plate. What is the plate? Quarter wave plate. I will take the thickness of the calcite crystal with having all principal section in it. Okay, whose thickness is such that it introduces, okay, introduces a okay, path difference, introduces a path difference of lambda by 4, or you know delta phase difference is equal to 2 pi by lambda into path difference. You know it already from interference chapter. So this is 2 pi by lambda. Okay, path difference we are getting it as, suppose say I'll have lambda by 4. I'll take it as. So you can calculate this, okay, as lambda gets cancelled, 2 gets cancelled 2 times. So I'll get pi by 2. That means a path difference of lambda by 4 is equal to a phase difference of pi by 2. Therefore, I say here, okay, introduces a path difference of lambda by 4 or a phase difference of a phase difference of pi by 2 between what? Between O ray and E ray. Okay, between O ray and E ray within the crystal. This is, of course, we have to say it. Okay, is called quarter wave plate. So quarter wave plate is nothing but a quasi crystal cut. That's all only of a required thickness. Quarter wave plate. So I'll draw this quarter wave plate. Then we'll write some equation, or you can write equation here itself also. What we are supposing is that now I consider here a quartz crystal cut. So don't forget that it's a quartz crystal only. It is not a nickel prism. Okay, this is what I'm taking here. I now write this as okay quartz crystal. This is calcite or calcite calcite crystal slab or crystal cut, I said, slab of thickness T I am taking. Therefore, I suppose that the thickness of the slab, whatever I am taking, this is the thickness I am supposing. The thickness of the slab is T. This is the thickness. Okay. The T we call it as thickness. Now I make a light, a polarized light to incident on it normally. So I take here a normal incidence, a light is falling on it, okay, normally on this. So I just keep it here. This is normally I'm taking. Okay, otherwise I'll show it by a different color. So this is I take it, I'm drawing normally, it is falling on it. And of course, I say this is normal incidence along with the normal direction. Now, the light ray is incident is a plane polarized. This is the plane polarized light, suppose. Whenever light, and I also suppose that the optic axis, okay, is on the plane of the top surface. This is the optic axis I am taking. This is we call it as optic axis. Optic axis. But you know that any line drawn parallel to, okay, any line drawn parallel to optic axis is also optic axis, because optic axis only gives the direction. So this is the optic axis. This is the optic axis, means that optic axis is on the top surface of it. This is also an important one. Okay, to get double refraction and this action of this, optic axis should be okay on the surface, of this one. Okay, so I say on the surface, otherwise you don't get double refraction. Now whenever light falls on the doubly refracting crystal, it splits into O ray and E ray. So we have O ray. O ray will have in calcite, okay, you know it is a spherical wavefront, spherical. And E ray in calcite, we know that it is elliptical, okay, elliptical wavefront. So we have elliptical wavefronts. And also we know that if you take velocities, okay, the velocity of E ray is greater than velocity of O ray. These are the velocities. Therefore, the E ray moves faster in the crystal than O ray. Therefore, I write now that E ray, okay, optic axis at the top, therefore the ray is going down. Hence, this should be a ellipsoid, something like this. This is an ellipse. So if I go on like this, I'll get, of course, an ellipse, something like this, somewhere here. This is the ellipse. I'll get ellipse. But they should touch along the optic axis. So what we are taking here is, this is the crystal cut I am taking. Okay, this is up and the crystal is extended something like this. Okay, therefore the waves are going inside it. The optic axis is at the top. Therefore, if I draw the E ray should move faster, and when I take the ordinary ray, they should touch each other here, but it should be a circular one. So therefore, if I make it, I'll get a circle here. And the black one which I'm showing is O ray, which is moving slower, and the pink color ray which I have shown is here is E ray. So thereby what I say, we have E ray vibrate, okay, dots parallel lines for these are the okay E-ray vibrations. They are parallel to the principal section and they'll come out. Because E-ray is moving faster, it will come out first out of the crystal. But O-ray is moving slower. As it is moving slower, it comes after some time. So as it is moving, see the difference is there between these two rays, that is O ray and E ray. E ray goes faster and therefore it comes off the crystal first. And after some time, okay, with a difference of maybe lambda by 4, because thickness we have chosen, the E ray will come. Hence, okay, O ray will come. Hence, E-ray moving faster will come out of it first. E-ray will come first. And after that, okay, O-ray will come. Hence, we can make a difference between O-ray and E-ray arrivals or transmission ones. Therefore, that depends on how much thickness you are taking it. So, okay, so we look at this in this case that suppose say I write here the path differences. So if you want to write the path differences, I write that okay, the path difference T is the thickness. I suppose say T is the thickness of crystal cut or crystal slab, whatever you're taking. And I suppose mu naught is refractive index of O ray, refractive index of O ray I am taking, and mu E is the refractive index of E ray. I'll take it. Now the path difference I have to take it. You know that optical path difference is nothing but the physical thickness into refractive index. Therefore, I write mu naught T, if I take it, is the refractive index of O ray multiplied by T, and the difference, because E ray is moving faster than O ray, I'll take it as okay mu E into T. Why I'm writing like this? Because you see here we have given that mu naught, that is the O ray, okay, is greater. This is greater, this is less. That's why I am writing the path difference okay, subtracting to get the path difference. So I write path difference is equal to this. Here mu naught is greater than mu E for calcite. If you take suppose a quartz, it is different. Okay, if calcite, then we have to write mu E minus mu naught. And this path difference for quarter wave plate, if you take it, a plate that introduces a quarter wave, a path difference between O ray and A ray. So for quarter wave plate, this is equal to path difference, whatever I take, must be equal to lambda by 4. Therefore, I write here that if I take it mu naught, okay, I take it as mu naught T minus mu E T is equal to lambda by 4. I'll write it as. So if I simplify it, I write mu naught into mu E into T is equal to lambda by 4. Otherwise, I'll write it T, the thickness what we require for getting a quarter wave plate is lambda by 4 into mu naught minus mu E. This is the formula for thickness of a quarter wave plate. This based on this you can do lot number of Okay, so I stop here, but can anyone tell me, what is, can anyone tell me what is the thickness of half wave plate by using the same procedure? Can anyone tell me? This is for quarter wave plate. Quarter wave plate. Now, can anyone tell me what should be the formula for half wave plate? So how do you define half wave plate? Yeah, roll number 22.
Yes, sir.
How do you define a half wave plate?
Maybe we should take lambda by 2.
Yeah, correct. So you have to take a
Lambda by
lambda
2.
by 2. Yeah, that's all. So therefore, E mu 0 T minus mu E T for calcite. For quad, it is reverse. Should be equal to what? Lambda by
2.
2.
Lambda by 2.
Yeah, then can you tell me what is the value of T?
Lambda by 2
Ah,
mu naught and minus mu e.
yes. Now, by using this logic, you can create any wave plate, not only quarter wave plate, half wave plate. Because if you want to make, suppose, say, lambda by 6 plate, can you do lambda by 6 plate? Lambda by 6 plate means, suppose, say, delta is equal to 2 pi into 2 pi by lambda into pi by 6. Okay, lambda gets cancelled. This goes 3. Then I'll get pi by 3. What is pi by 3? What is the angle? Pi by 3.
60 degrees.
Yes, 60 degrees plate also you can make. If you equate lambda by 6, you can make like not only quarter wave plate, half wave plate, lambda by 6 plate also you can calculate. Okay. So likewise, lambda by 4, lambda by 6, you can calculate it. These are the wave plates. What are the purpose of wave plates? You can produce circularly and elliptically polarized lights using, okay, using half wave. Half wave. I am not doing any derivation for half wave. I'm also not writing definition, but the question will be asked. Instead of explain the action of quarter wave plate, you have to write all the figures. Same figure you can draw for half wave plate also. Okay, same derivation you have to do it. Except lambda by 4 equal to path reference will become path reference is equal to lambda by 2. Using half wave and quarter wave plates, quarter wave plates, okay, elliptically polarized, elliptically polarized and circularly polarized, circularly polarized light can be produced. This is the application or use of half wave plate, quarter wave plates produced. Okay, so I stop here. If you have any questions, you can ask me. And the definition of quarter half wave plate you have to write in terms of just as we have written for a quarter wave plate. Just like that you can write. But you also see that this is for calcite. If you take quartz, it is a positive crystal. Then mu E is greater than mu naught. Then the formula will become mu me minus mu naught. Okay. Yeah. If you have any doubts, you can ask me. Otherwise, we will wind up the class.